So let's see, this is going to be interesting. You can do it there, buddy. Okay. Whoa, that's actually a little freakadelic. There we go. All right. So I want to do an example that I kind of lead into something we're going to do to get into section 6.3. So I want to do a disk example. Two of them, actually. So say I have y equals square root of x. And I want to go from, let's say, 0 to x equals 1. Right? We'll sketch that region real quick.
Is it 0 plus 0?
Two. X equals 0, 2.
Was like,
That's funny, I rewrote it and they're like, plus 0, okay.
I'm like, okay.
Nice check. So that's it, right? And let's say, so here's x equal 1. So here's the region that we're gonna rotate, right? I want to rotate around the x-axis. So if I'm going to use disks, what does my integral have to be? Integral dy.
Yes.
Yeah. Sketch the region, first step. Immediately figure out dx or dy, because that's going to control everything else you do. Okay? And let me see. I've sort of been relying a little too much on the computer. I'm not putting enough faith in my own drawing ability. But if I did rotate this, which you don't have to do, it would end up, you would get a bunch of these disks, yes? So I desperately want you to understand, when we're using the disk method, we're chopping the region up and then adding those disks up, right? How do I locate each disk? You guys see, what are the disks sort of moving on? How do I locate, like how would I locate this disk? Is it at y equals something, or is it at x equals something?
X.
Yeah, I locate it on the x-axis, right? Yeah? Okay. And that is why, because when I rotate around an axis, I'm making a disk with that axis in the middle. And of course, how would I find the next disk? I would move on that axis to find the next disk, which is why this matches with the rotation axis. Okay. I like it. So like I said earlier, I like to think of it as scanning along the x-axis. As I move along the x-axis, I keep picking up more and more disks, and I just keep adding them in. So that's the idea. That's all disk method is. What has to be, in general, on the inside for disks?
Pi r squared.
Yeah, pi r squared. D, whatever. So in this case, what will the radius be? So here's my arbitrary x. What's this radius? How long is that?
Six.
Say again?
Pi over x. Or no, sorry, rad x.
Rad x. Right? Okay, I like it because it started at 0 and I went to rad x. So this is rad x squared. Right? And what's it going to go from to, of course? You can't go wrong with this example.
0 to 1.
0 to 1. Either way you look at it, 0 to 1. All right, let me stop for a minute. Does anything about this not currently make sense?
Is that a pi that you took out?
Yeah.
Oh, yeah.
Because again, what's the only thing I can take out or put into an integral? Constants. I can't take an x variable out because that's what the integral is doing stuff to. Right? Yeah, I like it. Okay, so, and then you just have to do that. Right? The hard part is this and that and setting it up. Now it should be the easy part. So what do we get? Of course, that becomes
X.
And that kicks ass, right? But get out of here. What's the integral of x?
X squared.
When you put a 1 in, you get half, so you get pi over 2. When you put a 0 in, it's 0. So you get pi over 2. So that's kind of interesting, yeah? This bowl-shaped thing has a volume of pi over 2, whatever the units are. It's kind of nifty, no? A little bit, a little tiny bit gesture. Okay. Now, I want you guys to do the exact thing we just did, but I want you to do it for an even easier function. So I want y equals x from x equals 0 to x equals 1 around the x-axis. Again, you're doing exactly all the same stuff. Sketch the graph. You don't have to draw any 3D. Unless it helps you, right? Besides the graph, the only real difference is going to be okay. So now when I rotate it, it's going to look like a cone, right? Does that really matter? I don't need to do that because I know the radius will be from the axis of revolution to the function. That's the radius. Since the axis of revolution is basically 0, right? Y equals 0. That's easy. So what's this radius? Pretty easy. Right? Is that cool? Pi r squared, where r is x. And what's the integral of x squared?
Or x cubed over 3.
So I just get pi over 3. All right, now. Is that all right? Why does it make sense? Which one of these is a bigger volume? This one for sure, right? That's pi cut in thirds, this is pi cut in half. Why does it make sense? Because this bows out, right? Or how do I say it? It doesn't bow out like pi, it curves out. So now here's the trick. Some of you guys might know where I'm going with this. All right, ready? Here we go. What if I wanted to know the region bounded by y equals square root of x and y equals x rotated around the x-axis? Stay with me. Does anyone see how we've done all the work we need to do to pretty much immediately get this answer? And I really want to point out, so if we did this, it would be, here's the square root, here's the line, So this is the region. The textbook would call the method I have to use washers. Why? How do I know that? How do I know I need an inner and an outer radius? Yeah, it's not hugging the x-axis. Poor little x-axis. But do you see, how does this and this relate to what I got to do there? I really, right? Do you guys see? So this is why I say they should call it freaking washers. They should call it 2 discs or something. They should call it, yeah. So I could just do pi over 2 minus pi over 3 because I've already done all the work. But do you see how the method that we use, D whatever, in general, right? That is doing this minus that. Yes? Because I've got this outer radius that sets up this shape, and then I want to cut out of that. I want to subtract what I get when I do this shape. So I just end up with this thing rotating around. Okay. So that's kind of like a drawback to the disk method, and there's several. One drawback is I've got to really pay attention to know if I need outer, inner radius, or if I just need one radius, right? I got to really understand why that happens sometimes. Okay, I like it. Another drawback to the disk method is, what if my function would have been something I couldn't solve for y? Because if I'm going around the x-axis, this has to be dx, yes? So if they give you a function that you can't solve for y, that you can't get as a function of x, can you use the disk method? No. Because what has to be in here, if this is dx, this has to be a function of x. This one's easy because it's already solved for y. Right? But what if I gave you x equals y to the 4th minus y cubed plus 5y squared minus y plus 2. Any of you solve that for y, I'll give you 10 extra points on the final. Nobody perked up. I'm glad. You guys all understand. That's basically impossible. It isn't really impossible, but it's just freaking hard as shit. It looks disgusting as hell when you get done with it. But yeah, that's not going to happen. We can't. You guys understand what I'm saying? So the beautiful thing about disks, whatever I'm rotating around, x-axis parallel to the x-axis, y-axis parallel, it's going to be d that. Bam. And then that sets up everything else. So if we are going to come up with another method, if I needed to do this region around the x-axis, could I use disks for this? No. So whatever other method we come up with, is everybody with me on that? You guys cool with that? Because if I go around the x-axis, disks needs this. Can I solve this and get a function of x? No. So if we're going to make another method, it better freaking allow me to do dy in this case. Then it would be useful, right? If I had another method that allowed this to be dy, now I can just plug that shit in and go to town, right? Maybe. I really want you to understand the motivation for having another method. You're like, isn't disks enough? Holy shit. No, it's not good enough. We need some help. All right, now hold on to this. Make sure you've got this kind of drawn out because we're going to come back to that later. And I want to show you later, we're going to use the new method to do this problem and see if we get the same answer. What is the answer, by the way? Just using what we've got here. It would be pi over 2 minus pi over 3, right? Is that cool? This volume, cut out that volume. Pi over 6. Yeah, pi over 6. I love it. Good old LCDs. All right, so hold on to that. We're going to come back to that later today. So, yeah, let me do that. Yeah, why not? Okay. Let me see. Should I go to this? No, not yet. Ah. So what if I have, oh, that's gross. Yeah, sure. Y equal, let me think. It doesn't matter. Y equals some function of x. And it looks like from A to B. And it looks like, that. But I want to rotate this around the y-axis. Now, I didn't tell you what the function is, but what does your gut tell you? This function has to be something funky, right? It's at least some freaky ass higher degree polynomial because of all the turning points that are present. Are you with me? So more than likely, I cannot solve this for x. Because what would disks need? Disks would need what? Integral d what?
dy.
Y. Why? Because this is going around the y-axis. So of course disks are awesome. They're like, there you go. Whatever's rotating around is d that thing, right? So that's nice. But can I do it then? Can I use disks? No, I'm screwed. Damn. All right. So what's the whole idea of disks? Is I'm going to end up with some volume, and I just slice it into circles, and then add up all the areas of the circles. That's the idea behind disks. So now we're going to develop kind of a new method. And the neat thing about this method, all right, do you remember how we did, things are happening. Do you remember how we did the integral just of this area I've got drawn? Then we make a bunch of rectangles, right? So make a bunch of rectangles, and then we figured out the area of each rectangle and blah, 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 right? Blah, 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 blah. So this method's kind of cool because it kind of brings that back for a second. We're not going to suddenly do limit, summation, blah, blah. Don't worry about that. Just the visual is going to be the same. What if I took each of, so I'm going to rotate this shape around the y-axis, yes? It's going to look kind of freaky, but can you guys envision this? Isn't this going to be this circular region with like a hole in the middle? It's going to be bumpy on the top all the way around, right? It's like this giant lifesaver that one side of it got all crumbled off. Or no, I don't know what the hell you want to think of it as. Are you guys semi with me? The bottom's going to be flat because it's flat, right? Top's going to be bumpy. Okay, I like it. Some weird, very symmetric island with a big hole in the middle. All right. So, I cannot, disks ain't going to cut it. So I just need to cut this volume into a different shape. Does it have to be circles? Not really, no. Now it has to be somehow based on circles, but it doesn't have to be disks. That's my point, right? Why does it have to be based on circles? Because I am rotating it, so it makes sense that there's circles going to show up somehow, whatever method I use. Okay. So what if I consider this, take any rectangle, right? Take this guy. This rectangle right here. Let me erase the other guys. Go away. Okay. If I rotate that rectangle, and I've only gone halfway, so it's easier to kind of see what the shit's going on. And I kind of showed you this last time. What shape am I going to make if I complete that rotation?
So,
Not a disc, because it's not filled in the middle, is it? It's going to be like a soup can. You guys agree with me? Isn't that middle going to be hollow? Yes? So officially we call that a shell. A shell around something means that the middle's hollow. And it's cylindrical in shape. So this is a cylindrical shell. So if I completed this and I put it down here, it would basically look like this. All right, where this is hollow in the middle. Are you guys semi with me? Can you see that? So if I completed this and went all the way around, it would just be this outer shell in the middle is hollow, of course, right? Are you guys?
I guess they're ridges. Like on
Oh, yeah. I mean, here's the trick. How wide will this rectangle eventually be? ZX, in this case. Right? This rectangle will eventually be that line, yes? And the height is what's really going to matter. But all right, so this is a different method than discs. Let me ask you this. Does everybody agree with how I've drawn my rectangle? Doesn't that? Do you notice how the rectangle is parallel to the axis of revolution? Now let me ask you this. Has everybody got that picture sort of on your paper? Can you find another rectangle, just some other rectangle in the region? Just draw some other rectangle somewhere, right? Doesn't matter where. I'm going to put mine there. And how many of those rectangles are going to end up being there? Infinite of them, right? How do I locate each rectangle? Where do they all live? How do I find? How did you find another rectangle? Didn't you do this? Here. What did you move on to find another rectangle? Which axis? X-axis, yes. So I locate these rectangles on the x-axis. Yes? Feel like it? Stay with me now. So how do I locate discs? I locate discs along the axis I'm revolving around. Yes? That's why for discs it's dy. Because I would find my discs, they would live here. I would find my discs along that axis. For shells, I locate my rectangles on the other axis. That's why for shells, if discs has to be dy for a situation, shells has to be dx for that same situation. Doesn't that match up with what we just said? Another method better frickin' do, right? Are you guys semi with me? You know, like, I understand. Like, that's so freaking important to understand. Why is one dx and the other dy? Because it's how I locate the main thing I'm doing. How do I locate a disk along the axis of revolution? Because that's how I create disks. I revolve around the axis of revolution. How do I locate rectangles for shells perpendicular to the axis of revolution? Because I want to make a thing and then have it rotate around that. That is why if one is dy, the other one's dx. Now, if I take every shell that is created and I add all their volumes up, won't I get the volume of the freaky looking giant lifesaver thing? If I take every shell that I can make and I add, my drawing's horrible, but and I add the volumes of each shell together, am I not going to end up with the volume of the whole thing? It's sort of like, it's really like just taking this shape and finding the area. How do I find the area? Add up all these rectangles. Now just rotate that, you know, of course I'm going to end up with the volume of the thing because I'm basically just doing, revolving the region strip by strip. So of course I'm going to end up with the volume of the whole thing. Okay, maybe. So I love shells because it basically looks like what it looked like when we were doing integrals, rectangles, and add them all up. Now we're just adding in a revolution on top of it. You say you want that something. Now, when I understood disks, I had to add up their areas, correct? And really their volumes, because dx was the width, but it was all pi r squared. It was their areas, really, that we're looking at. You with me? All right. Now I want to do the same thing, but I want to add up every single shell volume. So don't I have to first figure out what the hell the volume of a cylindrical shell is by itself, so then I can write an expression so I can add them all up? Disks was easy, pi r squared. Woo! Right? I don't know if you guys remember, if I cut this thing in half and open it up, it'll look like this. Do you guys agree? If I chop it right here and open it up, chop it, right? I really want you guys to not just accept what I'm saying, but understand that is the reality, yes? Because if I take real quick, I know most of you guys are with me probably, but if I just take this and, oh, it's a cylinder! Holy shit! So if I, it's a rectangle, okay. All right, that's all I'm saying. So let's identify a few things about this cylinder as a radius, yes? Where's the radius on the picture? Look at this cylinder right here. What's the radius? In fact, the funny thing is we do the same thing. Where's the axis of revolution? Y-axis, yes? So I start there, and I go out until I hit, well, in this case, X, right? And of course it's got to be X. I know I have two X's right now, but X takes on all the values. So if I let X go from A to B, which is what the interval is going to do, I will take every single shell and add them up. So how do I always do radii? Well, I start at the axis of revolution, and then I go out until I hit the thing. Right? For disks, it was the wall I was hitting. For shells, it's the location of the rectangle that I'm hitting. So in this case, what's the radius? X. I love it. Because if X is this thing, then that's the radius for this guy, and so forth. Okay, that got shitty. Oh, do that. So, I got a radius. I got a height, right? What would the height be here? How tall is this? Ah, cool. So for disks, the radius was related to F because that was the wall I was hitting. For shells, the height is related to the function value. Just like they were when we first learned intervals. The height of the rectangle was the output at that point, F of xi. Okay. And then tell me this, what's this distance? If that's r, what's this distance around? Let me do this. What's that distance around? 2 pi r, which is the derivative of pi r squared. Interesting. So where is all this shit there? What is this? You can do it. So if this is, all right, what's the distance around the circle? 2 pi r. What's it become now? It's a rectangle. No, it's still 2 pi r, but now it's the side of the rectangle, right? And I should have been doing it like that, but so this is 2 pi r. Isn't that this? That is this. So of course, if I just open it, I don't suddenly make it bigger or smaller. It's still the same 2 pi r. And what is this? H, which of course, yeah. But so right now we'll do this, and then we'll get it related to this. So what's the, and of course this, what did I say earlier? How wide is that rectangle going to be? Dx. So what is the area of this rectangle? 2 pi r h. And to get the volume, I just multiply by, isn't volume length times width times depth? And that is a, let me call that a volume element. What do I call this dV? Because that is one volume element, and I want to add up all across them. So to get the volume of the end result, I just add up all the volume elements from A to B. Freaky shit. Just the same way when it was pi r squared inside, we just add them all up. And what does add them all up mean in calculus? Because I'm doing a sum of an infinite number of things. Integral. That letter again, what's the integral of letter? What's the integral letter? What did they stretch out to make the integral sign? S. Never forget that. It is telling you it's a sum. That's what the integral basically does. It sums stuff up. That's what it does. Now I can interpret the result as area and all this other shit, but it's a big old freaking S, so it's in your face. It's the sum of shit. And what am I adding up now? I'm adding up a bunch of these shells as I move along. All right, so what would this look like? Let's see. For this specific problem, well, it's not very specific, is it? Oh, well, sort of semi-specific. So that would look like A to B, right? So I know it's dx because it's shells. And the way I would do it is I would first think, what would disks need? Can't do that shit. Shells is the opposite. Do you understand? Disks is easy. Whatever I'm rotating around parallel to the x-axis, dx. Parallel to the y-axis, dy. And then I go, oh, that's not going to work. Well, I'll try shells, which is the other thing. Other thing? Sure, what? And what is x doing in this picture? To capture the whole region, x is going from A to B. 2 pi r h, right? So I can take a 2 pi out. What did we say the radius was? X. And then the height. Now, of course, I could rotate this whole thing and have it be a function of y, in which case it would be 2 pi y f of y dy. No? Yes? Couldn't I have done all this rotated so it was hanging off the y-axis? If my region had looked like this, then all the work we just did would have led to no, yes, is that right? Is that right? I mean, I really want you to understand, on one level, x and y are dummy variables. It don't matter with shit. I can make one the other one easy, just rotate the whole damn thing. So I did everything here in terms of x. Well, if I just rotate it, then everything's in terms of y. Whoop-de-doo. Right, so I just want to show you, shells could be dx or dy, just like disks, right, depending on what it's a function of. All right, so let's do a concrete example. What do you guys think? Would that be nice? Okay. I guess so. All right. What do we think? Do I want to do this one? Yes, let's do this one. This is fine. So another, not as colorful, but still, it's like 2 colors on it. 3 colors on this thing. Count blue and beige and the black for the letters. All right, so let's take a look. All right, read through it a little bit. Try to do the first thing it asks you to do. Some of you guys might realize, where it's headed, but still try to do it. See what you end up with. Now I gave us a specific function. It's always nice. Is it a nice function? Your correct answer is yes. I really want you to understand. Whenever I'm trying to integrate or differentiate or whatever, I do not give the first shit about constants. I care about the actual function of x. And this is polynomial. Are the numbers nice? No. So I stole this image from a book or something. and then I tried to create a function that roughly came out to be this shape. So that's why it looks kind of funky coefficients, right? That's what I call backwards engineering. So if you try disks, what's the most important thing to first do? I've already got the region sketched. Oh shit, Jeff. What have I done? Okay, I've got the region sketched. So what is the next thing you do right after you sketch the region? What's the very next thing you do? You're like, all right, let me try disks. What's the very next thing after sketching the region? What's the very next thing you do?
Integrate it?
And well, you set up what the integral needs to be, right? Integral d what?
Yeah, if you want.
Which one is it here? Disks would need integral dy. My function currently is a function of what? X. It's y equals stuff with x, so it's a function of x. Again, can you solve that for x to make it a function of y? All right, do it.
No.
All right.
You
I can
said
solve
it's-
that function in 3 steps.
You said it's not impossible. I don't want to do it.
All right. Yeah. No. It's like immediately next to impossible. It's that gross.
Okay.
Yeah. And the cubic function is disgusting. Because you know the quadratic formula and all that kind of stuff. There's also a cubic formula, but it involves imaginary pieces and roots inside of roots. And does that sound like a function you want to try to integrate?
I don't care.
All right, so even if we technically could solve that for x, I end up with a function I wouldn't even be able to integrate anyway. Okay. Is everybody with me on this? So 6.2 is disks and washers. 6.3 is shells. What's going to happen on the test? I'm going to just give you a problem, and you have to fit which one do I use, right? That's how it's going to be. So I always start with disks because it's the easiest D thing to figure out. Y-axis, dy, oh shit. That's why you then say give up on disks, right? You can immediately give up on disks. You guys kind of, so you don't have to know immediately when you first read it, disks or shells. You don't have to. Set up disks. Is it possible? No. Okay. Not a big deal. So here is what I was attempting. Now I think I did, especially considering my artistic talent or lack thereof, I think I did an okay job here, maybe. You guys don't have to butter me up or anything. You can be like, it was passable. But that's basically what I was trying to do right there, right? I take a rectangular region anywhere in here, I'm going to rotate it, which is what I'm going to do with the whole region. So of course if I do that for every single little dx in here and do it, I'm going to end up with the whole shape. What it would look like at the end, a little flying saucer view, right?
Looks like a Reese's peanut butter though. I don't know why. That's the
All right.
second thing
Where some vampire sucked the middle out. It's pretty strange. Vampire, but I'm not going to...
People, I don't doubt at least one person does that.
Yes, I'm not going to judge others by their Reese's Pieces habits or Reese's Bells habits.
Well, I will.
All right, and then here, all right. So this is just to give you a better computer-generated image of what I was trying to do on the board. Right? I mean, if I do every single possible one of these and add them up, I'm going to end up with this full volume. So I desperately want you to understand how, when we first introduced area and we said, okay, here's a rectangle, let's add up the areas. We're doing the same damn thing, except now, here's a shell, let's add up the volumes, we get the total volume. It's the same exact thing. All right, so help me out. Here's what you got to do. You don't have to draw any, where you're going to try to say, you don't have to draw any 3D, right? You don't have to. Where's my axis of revolution again?
The
The y-axis. I'm going to do this for myself. A little quick visual. I can always kind of look at it to keep myself straight. How do I want to draw my rectangles in them? Do I want to draw them laying down or standing up? So, do I want to draw it in like this, laying down, or do I want them standing up? Which way? standing up, because they have to be parallel, so that they can then go around the sucker. Does that make sense? Okay. So draw in, just pick a place and draw in a rectangle. I'm going to put mine here. Okay. So what do I need to identify? I need to identify the radius, and real quick, it will not always be this for this situation. Isn't it, what is it for this situation? It is, how do I locate another rectangle? I would just go further on the x-axis. So this will be this radius, right? Draw on the radius. The radius is from the axis to the rectangle. Of course, how long is that radius? That's some arbitrary x place, but R is x. So R is x. Why would the R, go ahead, Tom.
I don't think I have this paper that we're using right
Oh. I just gave it out.
Yeah, it was in the back.
Oh, yeah, that'll do it. All right. And of course, the height, and I want you to draw that damn rectangle in, please, because it helps me figure out the radiuses. And of course, how tall is that rectangle? Well, it goes from the 0 line up to the function, right? So it is this. Yes? Okay. So real quick, what is one thing I could do so that the radius is not x? The radius has to be the distance from the axis of revolution to the rectangle. Rectangle is going to be sitting at x. So when would that radius not be x? Well, I could say the axis of revolution is x equals 1. If the axis of revolution was x equals 1, what would the radius be? X minus 1. Big minus small. With me? If I would have made it negative 1, x minus negative 1x plus 1. The radius. So the only time the radius won't be x or y for shells is if the axis is not x or y axis. It's like off axis. Does that make sense? If you're rotating around the x-axis or the y-axis, shells will have x or y just sitting there for R. It's beautiful, right? Now coming back, what's f? What's the height? The height is going to be the f of x, right? So let's put this thing together. So we're going to integrate from what to what?
2 to 4.
dx, right? Say again.
2 to 4.
2 to 4, I love it, because that's where the region is. 2 to 4, put my 2 pi out front. X times f of x. And there. Is that cool? Just throw the old function in there. Now, of course, you distribute. So the rest of this stuff is easy, sir. Right? I know there's decimals. I don't care. What's the integral of something x to the 4th? Yeah, something x to the 5th divided by 5. I don't care. Right? I don't care. I don't care. Minus integrate x cubed. 5x to the 4th over 4. Plus integrate 14.9x squared. It'll be 14.9x cubed over 3. Is that cool? Right? The constants aren't giving me any trouble. Of course they're not. I don't care. They just come along for the ride. Minus 11x squared over 2, evaluated from 2 to 4, and here's where I don't care really. I mean, now you just plug 4 and you plug 2 on your calculator, who cares? Especially on a problem like this. I'm not going to make you do this crazy thing by hand. Just throw it in a calculator. Maybe? Maybe? Okay. So in a lot of ways, cylinders is better than discs. There's no square. Discs have squares in them, which makes things kind of gross, right? If you had a parabola, quadratic something, you had to square it, it's going to, right? But of course, has some downsides too. Okay. So real quick, all right, let me do this. Coming back to that first problem we did. Okay. And you guys have it all there for me so I can ask you to remind me what this shit was. So we already knew the answer. Remember the very first problem we did? We did it in parts, but essentially the problem was y equals square root of x and y equal x equal 0 to 1, right? Around the x-axis. It's an interesting letter. Right, that was the very first problem we did. I did this part, and then I did this part, and then I subtracted blah, 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 blah. Okay. So I have this region here. Let's do it with shells. Not because we have to, but because we can. And I want to make sure if the shells does not end up with the same answer, then we can throw that, you can rip that section out like it was freaking Dead Poet Society shit. Rip it out and say, no shells for us, ah! So now I'm like, shit, Jeff, don't make a mistake. The answer was pi over 6, is that right? From earlier? Okay, so let's keep that in mind. Pi over 6 was the answer. So no matter what method I use, it's the same frickin' shape. It better come out to the same frickin' volume, yes? So if I'm gonna use, so discs would need what? Dx. You're thinking ahead maybe, right? Discs would need dx. You can look back and see that's exactly what we did. So if I'm forcing you to use shells here, which I am right now, then what would shells be? Yes. So do you understand what I mean by start with discs? And if either it doesn't work or I'm forcing you, or the book is forcing you to use shells, then you know shells is going to be dy. Okay. So I'm rotating around the x-axis. Let's see if you guys are cool with this. How would I draw in a rectangle? Would it be standing up or lying down? Good. Oh, sorry. Was that too? Oh, sorry. I just heard it came over. Thank you. Lying down, why? They have to be parallel to the axis of revolution. So then I can rotate around it, right? So if I draw in a representative rectangle, it'd be something like that. So the height goes like this now. How do I locate that rectangle versus another rectangle? Here's another rectangle. Here's another rectangle. How do I locate them? On what axis are they located? Yeah, the y-axis, right? So let me pick this one right here. That's y. Let me stop for a minute. Now, have I drawn any 3D? Nope, and I'm not going to. Because I don't need to. I want to remind you guys, you don't need to draw 3D. Thankfully. Now, if you can, if you're really good at drawing, then, freaking show off some. Go ahead. So what's the radius going to be? Start at my axis of revolution and go out until I hit the rectangle. What's that? Y. What else do I need to know? So let me put in here, I need 2 pi r height, right? Now here's what gets neat. It's the first time we're seeing this. What is the height of that rectangle? What's the top of it? Be specific? think, I couldn't hear what you said.
I said F of 1.
Oh, I see what you're saying. No, be specific.
Oh.
What function is that? What's the, do you guys agree with me that that's the top, the side is the top? Because you have to look like this, of course, right? So what is that? Yeah, y equals x, right? So it's a function of y now, so I better make this x equals y. So what's this? Why do we know it's a function of y dot a?
What, x equals y squared.
dy, right? So this top is x, and what's the bottom?
Oh. Y squared.
What's x equals y, that means that. X equals y, and the bottom is x equals y squared. So what is the height?
Y squared minus y.
What's the top?
Y minus
Y.
squared.
What's the bottom? Y squared. So it's y minus y squared. I think our brains say y squared is bigger than y. But is y squared bigger than y here? No. For things between 0 and 1, y squared gets smaller than 1, right? That's why a parabola kind of does the dip down and then it goes up. All right, let me stop. Did I have to worry about inner outer radius? Because I'm building my rectangle right on my region, so when I rotate it, it won't include the frickin' extra, like, empty space. Space? Sure. Do you guys understand what I'm saying? I don't have to, when I'm doing shells, I'm not gonna include the empty space at all. So why would I have to worry about subtracting anything? I'm not including it in the first place. I'm just taking, bam, that little thing, I'm gonna rotate it. So I'm not including the empty space. In the first place, I don't have to subtract anything out. Why was it different for the other problem we did? Because the region was hugging the axis, so the height was the function. Well, here the height is the difference in the functions. So now I can put everything together. This will be 2 pi integral from what to what? This is dy, so this problem is a little bit bad about that, but I look at the y-axis. They happen to both be 1, but you understand, if you're doing dy, you gotta look this way. So 0 to 1. What's the radius? Y. And what's the height?
Y minus y squared.
So I get 2 pi, well, let's keep this. Integral 0 to 1, y squared minus y cubed. I'm just going to do this real quick. Y cubed over 3 minus y4 over 4 from 0 to 1. I get 0 is 0, so just put 1 in 1/3 minus 1/4. And what's 1/3 minus 1/4? 1/12, and the 2 and thing, and it can become pi over freaking 6. Holy shit! Yay! Of course, it's the same stupid answer. It's the same stupid volume. Okay. Now, of course, this is fresh. We just learned this. We're not going to feel comfortable with this. I do, because I've been doing this since 1990, whatever. Right. You guys have been doing it for, I don't know, 3 minutes or so. So, let's look at the other side of that sheet. So I've got a mixture of things on the other side. Look at that very first problem. Can you identify shells or discs for this guy? So what steps do you take to try to identify that? What would discs need here? Well, discs would need integral d 1. Because I'm going around the y-axis. I know you're thinking the other way, but always do this. Write down what discs would need. You're not saying it's going to be discs. You're just writing down what discs would need. Can I give discs what it needs? No, I can't, right? Because how would I get what discs need? I need to be able to make that a function of y. And like we said earlier, you technically could, but you never want to, right? I ain't going to solve that shit for no freaking x. Right? So now that we know the other method, that doesn't mean I'm screwed. It just means I don't use discs. So now we've established shells, and we need dx. right? Got it. So shells, it's gonna be 2 pi integral a to b r h d x. Disks need something I can't give it. Shells would be the opposite. Okay, I got a chance here. Now, let's see. Can you guys sketch this? Can you guys give me a sketch? Give me a sketch. You know what to do with this. Come on now, it's just screaming for you to do something to it. Maybe? Of course, you could always back yourself up by using your graphing calculator, but you should try to do it by hand first. When I'm trying to graph something, what's like some of the most important points to find?
Zeros or intercepts?
Yeah, intercepts, right? Now I want to be in I want to be in the first quadrant, right? So let's find the x-intercepts for this thing. How do I find the x-intercepts for this? You good? Or there's 4 terms, so I can just group. Special place in my heart for synthetic, but it's like one of my teachers said, it's like trying to open a walnut with a sledgehammer. It's a little more than we need. What comes out of these two? Negative x squared. X minus 5. I always tell my students to put a 1 here. If nothing comes out, a 1 always comes out. So then I get x minus 5 times 1 minus x squared, x minus 5 times 1 plus x times 1 minus x. So what are the x-intercepts?
5,
Negative
1 is negative 1.
Yeah, which one do I not care about?
Negative 1.
Yeah, it's not in the first quadrant. So let's see, what is this thing going to look like? So I have an intercept at 1, intercept at 5. Let's put in the value somewhere in the middle. When I plug a 2 in, what do I get? I'm going to do it here because it's easier. I get negative 3 times 3 is negative 9 times negative 1 is 9. So I'm going to be up here somewhere. So it's going to look like this, basically. And then it's going to go, so remember what a cubic looks like. Let me think. What are you going to, oh yeah, because it has another thing back here. So it looks like that, and it's going to go forever down. So all I care about is this, because I wanted first quadrant, right? So if you have a ton of trouble doing it by hand, you can always back yourself up with the calculator, that's fine, but I might ask you on a test, I want to see your work, but you know, if you're like, I can't do this shit and I want to keep going, just do any calculator real quick. It's not the end of the world. How did I know it would be that end behavior? You guys see that end behavior? Remember that term? Why is it like that? It's negative cubic. I like it. So cubic normally goes like this. Negative cubic is like that. That's exactly what it's doing at the ends. Kick ass. Do you see how pre-calc was supposed to give you the little things you need to be able to do sketches quick? So I don't need an extra shit. I just need from 1 to 5. That's the only part of it that comes above the only part of the Loch Ness Monster we can see there. Right? So we'll drop decimals. Alright. So now that we got that figured out, and we're going around the y-axis, how am I going to draw my rectangle, my representative rectangle? Standing up or laying down? Why standing up? Parallel to the one I'm rotating around, right? Don't worry, it's just hold your guys. Oh crap, now I got that movie in my head. I'm going to just pick here. It doesn't matter where you pick, just anywhere in there, right? The axis is the y-axis. If I draw all the way out until I hit my rectangle, how far did I go? X. So the radius is x. What else do I need to figure out? The height. And the height, of course, is just
That's
f of x over not gonna write the whole damn thing here, but yeah, whatever the function is, and we know what it is. I guess, to me, shells is a little better in a way, right? Sometimes I think about teaching shells first, but that gets a little weird because the book's all set up for the other way around. But shells comes right off of drawing rectangles in the early part of chapter 5. It feels exactly like that, just letting it all rotate, right? So can you put your integral together? So it'll be 2 pi. I know I'm dx, so what is x doing in the region going from 1 to 5? Right? See that? X is going from 1 to 5. My radius is x, and my height is the function. Oh shit, you can't see anything. I guess that's important. Right? Do you guys see how I really need you to see the physical nature of this problem, that you can actually think of it physically. It is a shell, it is a rectangle, it sits somewhere. This isn't some, because when I don't know if I told you, but when I was taught this, I sucked at it. I was terrible at it because my teacher didn't show me any of the freaking geometrical ideas. And I'm like, now that I'm teaching, I'm like, how in the world could you do this at all if you weren't thinking about what this kind of does and locating a rectangle and all that kind of shit? Anyway, sorry. He was fun. He's a nice guy. All right. And now is the easy part, right? Now's the part I actually kind of lose interest. Well, you of course have to do it. You would first distribute the x, right? And then you can integrate, and polynomial is the easiest freaking integral you'd ever want to do. So if I brought that in, all the powers would go up by 1. Let me just do that. And then when I integrate, I get negative 1/5 x to the 5th plus 5/4 x to the 4th plus x cubed over 3 minus 5x squared over 2. And then I just got to plug a 5 in and a 1 in, and I don't care. Now don't interpret me not caring with, oh, we don't have to do this. Right? Just do it real quick. Who cares? You got a calculator? I don't care. Could this come out negative? Never. This is a physical volume. Comes out negative, don't make that thing. You will destroy the universe, right? I don't know what that would mean. Okay. It's like the evil containment jar. Evil containment. All right. Now, just look at number 2 and look at number 3. Don't say anything. See if you can identify disks or shells for each one. Just only do that step for 2 and 3. Who thinks they know which method 2 needs? That's where you gotta be real careful. Does it need dx or dy? Dx. Don't say dy just because you see a y. Y equals -2 is parallel to what? Right? X-axis. Are you with me? Okay. And of course, to be really honest, that's why the first thing we do is sketch the region and then put the axes down, and then that's an easy question to answer, right? But about y equals -2, that's parallel to x-axis. It needs to be dx, and does that match with what we have there? Yeah, so it seems like disks should work. Okay. And by the way, do you notice if disks doesn't work, shells will, and vice versa, but they sometimes both work, because we just did an example where they both work. So if the functions are nice enough, either way is going to work.
When will they work? When will they, like, when will
The
they-
only time they won't work is if it's a method we don't know what to do. And I was talking to somebody earlier. What calculus does is it gives you a toolbox. And for example, with integrals, we put one tool in there. You've got this big ass toolbox, and you open it up, and you got this little screwdriver, right? That's U sub. You with me? You got one tool. So if U sub doesn't work, does that mean it's not something doable at all? No, it just means you have to take Calc 2. Because in Calc 2, you get a wrench and some pliers and you get some other shit, right? You get some hex stuff and you get some whatever, right? Sockets. Ooh. Are you guys kind of with me? Does it make sense? So again, for us, some integrals just won't be able to be done at all because we haven't learned the method they need. But if one doesn't work, the other one definitely will. We just don't know the method yet, maybe. All right. So 2 is disks. What about 3?
Wait, 2 is shells, right?
Yeah.
Oh, wait.
So this needs, what would this need for disks? Integral d y. This is functions of x, but is this something we can integrate? So that's the other consideration. If you try, all right, let's do this. All right, how much time I got? Not much. Let's look at number 3 first real quick. Let's sketch this region first. So it's bounded by this and this and this. Oh boy. So how the hell do I graph that? What's x equals 0 mean?
The
Y-axis. I love it. So this region is bounded by the y-axis. By y equals 4. There you go. And then this function. So one wall is this, another wall is here at 4. This function, how do I graph that function? I don't know. So let's see, let's try. What if I make x 0? What would y be? Also 0. So there it is there. What if I make x, it's nothing really beautiful I can do. So watch this. Y equals 4 and y equals this. That's my 2 functions, right? How do I find out where they meet? Because I want to know where it meets y equals 4. It's going to be one wall. Yes? Make them equal to each other. Do you want to do that? No, but too bad. So if I make 3 natural log of x plus 1 equal to 4, you solve that. Sorry, there we go. So divide by 3, natural log of x plus 1, 4/3. What do I do next? What's the base? E. So e to the 4/3 equals the inside. So x equals e to the 4/3 minus 1. So when this is e to the 4/3 minus 1, that's 4. Alright, let's stop for now. I mean, can you guys see? One wall is 3 natural log of 1. Another one's y equals 4. 2 functions. One of them happens to be constant. How do I find out where they meet? Set them equal to each other. What I'm desperately trying to see if anybody will bring up is, if I try to use disks, aren't I going to get the integral of the square of a natural log function? Do we even know how to integrate natural log of x? Does anyone know what the integral of natural log of x is? I do. No. we don't know. We don't know. That's the very first thing you learn in Calc 2. Is how to, well, one of them is integrate natural log of x, the method to do that. So I'm not going to want to use disks. Now here's a different reason on this problem. Why don't I want to use disks? Because the function I've got, when it's a function of x, I can't integrate it. I don't know how to do it. So what if I instead tried shells? So discs would need integral, oh, what am I doing? It's the y-axis, Jeff. So I'm thinking backwards. All right, discs needs integral dy, correct? And that basically, and do you see how my function is a function of x currently? So shells is the one where it would be integral dx, and I have to have the natural log, and I can't do that shit, right? Discs needs dy, and can you guys solve that for x to get a function of y? Isn't that going to be like e to something? Isn't that a kick-ass thing to integrate? E to something? All right, so let me make sure you guys are all with me, because I was thinking I wanted to, and I forgot it's around the y-axis. The y-axis, discs with the integral dy. You might think, oh, then I don't want to use discs because it's a function of x. But that function of x sucks. It sucks. I can't do the integral. So let me solve for x, because then maybe I could use discs. It needs dy. Let me solve for x, get a function of y. Could somebody, we already basically did it. How do I solve this for x? Not yet.
Or divided by 3.
Divide by 3. Then you do what? And then I'm going to subtract 1. Is that cool? This is a y up here. You guys see it? Now watch. Doesn't that look like this? What do I get when I make y 4? Y equal 4. Don't I get e to the 4/3 minus 1? All right. So there's two really nice things that happen here. If I had to do dx, wouldn't I have to go from 0 to this thing? But since I'm doing dy, I'm doing discs, yes? Because that's the one that lets it be dy, which is the better function to use. So I'm doing discs. So what do I need to identify for discs? I need integral, I need pi, I need what inside? That's right, r squared. Thank you. I know nobody said that. Right, that's what discs are. There's pi r squared. So how do I figure out what the radius is? Is there going to be an inner and outer, or what situation am I in? I'm rotating about what? The y-axis.
It's going to be 9.
Isn't that hugging the y-axis? Well, that kicks so much ass. So what's the radius going to be? Yeah, radius is f of y. And f of y is this thing. Now here's where some of you guys might get discouraged. What am I supposed to do to r? Square it. And what am I going from to now? This guy controls you, sort of. Not really, because we're the ones that picked it. But that guy tells you everything. The inside's got to be a function of y. The limits have to be what y is doing, and what's y doing? 0 to 4. Kick ass. And again, if I did draw in a disk, wouldn't it be there? And the next one would be here, and the next one would be there, and the one before would be there. And so don't I move along the y-axis to gather my disks? Which is why I go from 0 to 4. All right, so is anybody concerned about this? How do you FOIL that thing? Well, it's e to the y over 3 times e to the y over 3. What do you do with exponents when you multiply like bases? Add them. So e to the y over 3 times e to the y over 3 is e to the 2y over 3. No big deal. All right, I'm going to FOIL this thing out, right? So I get e to the 2y over 3 minus e to the y thirds minus another e to the y thirds is minus 2e to the y thirds plus 1. Is that cool? Let's just try to be a y here. Now let's see who can do this. What is the integral? And again, if you need to, you can write that twice. You can kind of keep yourself straight, right? FOIL that bad boy out. Is everybody with me? Are you guys doing all right? You're all like, yeah, I'm doing really good. Class is almost over, Jim. I'm getting my class is almost over energy. All right. What is the integral of e to the 2y over 3? I do not need u sub. U sub is bullshit for this. I don't need it.
3 over 2y.
Yes, so it's going to be itself, but then wouldn't the 2/3 have to pop out when I take an integral? I mean a derivative, so wouldn't I have to put a 3/2 to kill it? Oh, don't forget my pi out front. Right, the integral of e to something is itself, but then you got to kill the part that chain rule would want to be there. So what's going to happen to this guy? Dang it. Yeah.
3/4. That's 6/4.
6 e to the y over 3. Like it. So over 3 would try to come down, so you must have had 3 times that on the outside to begin with. And then, of course, I'll do the last one plus 1. Hold on. And I want to go from 0 to 4, and this is the part I don't care about, especially this one. Good Lord. Just plug 4 in. Well, no, here's a really good, now watch this. You ready? So happy this happened. When you see this, you guys automatically sort of ignore it. And I don't blame you because we use polynomials most of the time. What is e to the 0? Oh shit! So now you are going to get something when you plug a 0 in. You guys notice that? So don't say, oh, if one of them's 0, I don't care about it. That's if it's polynomial. If it's 0, it's 0. This is not going to make that or that 0. It will make them 0. But not these guys. Oh shit! You guys see that? A little bit? Oh man, that's enough. That's plenty. I think I did everything I wanted to. What's coming up? Our test is on the 20th, which is a week from today. Yeah. So Monday I'll have the practice test. And Monday we'll do more of this, and then we'll finish up chapter 6. The last section in chapter 6 is so nice. It's like a breath of fresh air. Yes. Okay. Oh yeah.